PSN College of Engineering and Technology. So earlier I have taken 2 lectures on electron probe methods, that is scanning electron microscopy and transmission electron microscopy. So in today's lecture, I will focus on atomic force microscopy, which is coming under scanning probe method. So in previous cases in SEM and TEM, they are electron probe methods. So when the electron beam hit the sample surface, so there will be numerous processes happening. So depending on the electrons coming out of the sample, depending on the nature of the analysis, or depending on the nature of the detectors we use, so the method, the characterization method will be different. So if you focus on secondary electrons or backscattered electrons, the technique will be scanning electron microscopy. So if we analyze other electrons like transmitted electron, so that will be used in the analysis of transmission electron microscopy. So likewise, a lot of secondary processes are there. By capturing the different types of electron, we can get different types of analytical data. We can go for energy dispersive X-ray or selected area electron diffraction and high resolution transmission electron microscopy, scanning electron microscopy. So they are all coming under electron probe methods. So here atomic force microscopy is categorized under scanning probe method, where the 3-dimensional images of specimen sample surfaces with atomic resolution will be acquired based on the rastering the sample surface or scanning the sample surface using specially designed probes. They are called cantilevers. So using that cantilevers, we will raster the sample surface, or we will scan the sample surface. So that will give you 3-dimensional images of the specimen surface. So this method was first developed by Binning et al. In the year 1985. So in atomic force microscopy, so mainly we monitor the force between the probe, that is the cantilever tip, and the sample surface. So that force will be converted into electrical signal using the piezoelectric materials. So that we will see in the next slides. So this method is developed mainly for characterizing the insulating samples. So in the earlier cases, SEM and TEM, we need conducting surfaces so that we can acquire the morphology or the images of the sample surface. So in order to analyze the insulators, so we need atomic force microscopy. So the thing is, the instrument will raster or scan the sample surface using cantilever. The force between the cantilever and the sample surface will be measured. That force will be converted into electrical signals. So before going into EAFM in detail, so we will look at the key features of scanning probe methods. So in the instrument, physical cushioning mechanisms, motion dampening eddy currents induced by the magnets and the copper plates, and a nitrogen gas regulated suspension system. So these are all served to isolate the scanning probe method from external variation sources, and there will be a computerized feedback system which will control the piezoelectric devices with nanometer level precision, which will guide the probe during its descent to the surface less than a nanometer above where the van der Waals attraction exert force on the probe tip, or tunneling current is able to flow in STM. So these two techniques are basically scanning probe methods. In AFM, we will monitor the force between the probe tip and the sample surface. In the STM scanning tunneling microscopy, so there will be a tunneling current which will be monitored between the instrument probe and the sample surface. Here the piezoelectric devices will monitor the force change or the forces in nanonewton level. So that much accuracy the piezoelectric devices will detect the force, and this scan will be the rastering of sample will be in nanometer scale. So then only we can obtain the images of the topology of the three-dimensional image of the nanometer sized particles. So in the case of AFM it will be force, and in the case of STM scanning tunneling microscopy, the output measurement will be tunneling current. So that will be magnified, or that will be changed to the changed into images of the sample. And there will be a computerized control of piezoelectric scanners which will be used for the movement of the probe tip across the sample and sample surface with nanometer precision. So that scanning method will be the rastering will be with nanometer precision. So that will be controlled by the computer. So the piezoelectric scanners that will move the cantilever tip over the sample surface, and the clarity of the image is based on is depending on the sharpness of the cantilever tip. So the fabrication of sharper probes allows for better resolution of surface features. So this is the sample images of cantilever tips. So whenever we have the sharp tip, so we will get a accurate image, clear image. So usually the probe tips are made up of the materials ranging from silicon to harder materials like tungsten. So basically silicon nitride Si3N4 will be used as the probe tip, will be used for making the probe tips. The resolving power of AFM and STM, the resolving power of scanning probe methods, instruments, depending on sharpness of the curvature. Sharpness is nothing but the curvature. Sharper the tips result in more clarity of the image. So the resolution of the image is highly depending on the curvature of probe tip or cantilever tip. So this is the picture of tabletop AFM, the computer controlled AFM instrument is there, control electronics stage. This is the overall image, and this one the main parts involved in the atomic force microscope, video microscope lens, through which we will see the images of the sample surface. AFM scanner, the piezoelectric scanners, they will move the probe tip over the sample surface to raster the probe on the sample surface, and the sample holder. So there will be a double sided tape will be there. We have to fix the sample over there. So we will see the operation in detail in the forthcoming slides. And Z motors, XY sample stage. So this represents the sample will be moved in X and Y direction, whereas the cantilever, the probe tip will be moved up and down. The sample stage will be moving X and Y direction, and the probe, the cantilever tip, will be moved up and down direction. So that in that way the sample surface will be scanned or rastered. So atomic force microscopy mainly for characterizing electrically non-conducting material, that is insulators. So this is the cantilever tip, probe tip, and this will be rastered through the sample surface. So this up and down area representing the sample surface. So when we operate this AFM instrument, this cantilever will move in Z direction up and down along X and Y direction, rastered along X and Y direction, so that the surface three-dimensional image of the sample surface will be obtained. So what the AFM atomic force microscope will measure, that is force in the range of nanonewton to micronewton. So this is based on the Hooke's law, F equal to minus k into x, the spring constant, and the distance between x will be the distance between the cantilever tip and the sample surface. So probe is normally made up of silicon nitride or silicon. So usually these kind of materials are used to produce cantilever tips. So this is the overall process involved in the atomic force microscopy microscope. So during the operation, the laser beam will hit the cantilever tip at the top of the cantilever probe tip, the shiny side. So based on the movement, based on the deflection in the cantilever tip, so there will be a deflection in the laser beam, so which will be monitored by the mirror and position sensitive detector. So whatever the deflection caused on the cantilever tip, that will be measured by the position sensitive detector by converting the deflection into force. So that force will be again converted into electrical signal. So there will be a control unit which will convert force into electrical signal, and that signal will be magnified in the as the image of the surface. So here these piezoelectric materials are there. Piezoelectric materials is used to convert any mechanical forces into electrical signals, or vice versa. So when we apply voltage, so there will be expansion in the piezoelectric material, the volume of the piezoelectric material, or if you apply any mechanical stress, that will be converted into electrical signals. That is a property of piezoelectric material. So this is a cantilever tip. Once again I repeat it. So when we when we pass the laser light on the top of the cantilever tip, automatically there will be a deflection in the laser beam after hitting the cantilever tip, because the cantilever tip is rastered over the sample surface. So there will be a deflection in up and down direction, in Z direction. So that deflection will be monitored through the mirror and the position sensitive detector. So that detectors will convert or the specially designed mirrors, they acquire the deflection in the laser beam, that will be converted into force. So this force again converted into electrical signal, that will be magnified as the image. So the signal from the photodiode detector is proportional to mechanical displacement of the cantilever. So how much deflection? So with respect to the deflection in the cantilever, so that is directly proportional to the signal what we are getting in the control unit. So deflection will be converted to force, force will be converted to electrical signals. So this is a whole process happening in the atomic force microscope. So what is the role of piezoelectric material? Piezoelectric devices are the dielectric components that are able to convert mechanical stresses into electrical signal. So this is what I told you already. So So it will convert mechanical forces or mechanical stresses into electrical signal, or electrical signal into mechanical stress, mechanical change. So when we apply the voltage to the piezoelectric device, there will be expansion, there will be a mechanical change. Or if you make a mechanical change, that change will be converted into, or the mechanical stress will be converted to the electrical signal. So that kind of property it has, the piezoelectric devices. So typically this material will expand about 1 nanometer when AC volt per 1 AC volt is applied. So therefore they accommodate to count all the variables of motion or to accommodate all the variables of motion required to map the surface of the sample. So to collect all the motion of the cantilever tip, or to collect all the changes occurring at the cantilever, the probe. So we need piezoelectric transducers. So it will collect the changes and it will convert into electrical signals. So that's why in the piezoelectric transducers are comprised of hundreds of layers in order to collect, in order to accommodate all type of changes. That will be converted into electrical signals. So the rastering can be done in two ways. In one, the sample is moved related to probe tip. You can move the sample by keeping the probe at a fixed place, or sample may be kept stationary, or while the probe is scanning or rastering through the sample surface. Either we can fix the probe tip or we can fix the sample surface constantly. The other will be moving in order to scan in order to get the images. So for most configuration, piezoelectric device controls the XY displacement of the sample and Z motion of the probe tip. So in most of the cases, the piezoelectric materials are used to move the sample surface in X and Y direction, and the probe tip will be moving in the Z direction up and down. So this is a normal case. So how is force measured and force between? So what kind of force is there in the cantilever tip, between cantilever tip and the sample surface? So this suppose a van der Waals force of interaction. It may be either attractive force or the repulsive force. So the minute force, that is weak force, van der Waals force, that will be sensitively monitored by the instrument. So the cantilever is designed with a very low spring constant, so it is very sensitive to force. So this cantilever tip is very sensitive to the force. So any change, any small force is applied on the cantilever tip, which will respond. So such a very sensitive tool which is placed in the AFM instrument. So the laser is focused on the cantilever, top of the cantilever. So the deflected beam will be monitored through the sensor. Okay, the laser will send the beam to the cantilever tip, and the deflection in the laser beam will be monitored through the sensor. So the position of the beam in sensor measure the deflection of the cantilever, which in turn monitor the force between the cantilever tip and the sample surface. That force will be equal to minus K multiplied by Z. K is the spring constant of the cantilever tip, and Z is the distance between the distance of the deflection of the cantilever. So this is scan direction. This is the cantilever tip. So it will move in X and Y direction. Here you can see the cantilever tip will be moving up and down, that is in Z direction. But but the rastering will be in the x and y direction. Rastering will be x and y direction. So while rastering or while scanning, the cantilever tip will be moving in z direction. So this is a piezoelectric scanner. One in a particular axis it will be moving, and the rastering will be through other two axes x and y. So these scanners are used to move the prop. Piezoelectric scanners are used to move the cantilever tip. So this is also one of the examples of piezoelectric material, that is palladium, barium, titanium oxide. So the piezoelectric scanner or piezoelectric material is made up of palladium, barium, titanium oxide. So this is actually happening while the cantilever tip approaching the sample surface. That is called the interatomic force. The force is interatomic force, meaning the force between the cantilever, the atoms present in the cantilever tip, and the atoms present in the sample surface. So how it varies with respect to distance. So in y-axis, distance is plotted. This is force. So when you have a very closer contact, so it is almost touched, the distance is 0. So there will be a higher force. This force is repulsive force. So when you keep closer both the cantilever and the sample surface, there will be a repulsive force. So automatically the force, it may be a repulsive force or attractive force. Anyway, the magnitude of the force will be higher with this region. So meaning the contact, and the non-contact force will be through in this region. There will be a in the middle of this distance, half of the distance in this graph. So there will be a non-contact, but almost closer to the sample surface. The cantilever will be closer to the sample surface, not touched, but somewhat closer to the sample surface. So there will be attractive force. There will be attractive force. So that's why in this picture we have clearly shown. This is the attractive domain. Here, this red line is a region of hard contact. This is touched. Both cantilever and the sample surface touch each other. And when the distance is higher, tip to sample separation at this region, so there will be no force at all, no deflection. There is a no deflection in the cantilever. So when you have the hard contact, there will be a deflection in the cantilever, position of the cantilever, because there will be a repulsive force. When you have this distance, still you have the deflection in the cantilever, the force will be attractive. And when you have higher distance here, tip to sample separation, so there will be no deflection. So this is the interatomic force and the distance. So there are three types of modes of AFM. One will be contact mode, other will be non-contact mode, and another one tapping mode, intermittent contact. So here I have shown contact mode AFM. In contact mode AFM, the cantilever tip always touches the sample surface while rastering through the surface. So this for soft sample, it will acquire a clear image. The cantilever tip will not be damaged through the scanning process. But while you go for the hard sample, there will be a bent in the or there will be a damage in the cantilever tip. The curvature will be damaged. So nature of the sample surface, we can go for contact mode or non-contact mode. So non-contact mode we will see in the next slide. So here the tip curvature will be 5 to 20 nanometer radius, and the height will be 10 to 25 micrometer height. And on the cantilever beam, 550 to 400 micrometer cantilever beam. So these are the specifications of the cantilever used in the contact mode. So it always touches the sample surface and raster through the sample surface. So contact mode measures always the repulsion between tip and sample, because they touch each other, so automatically there will be a repulsive force between the tip and sample. So force of tip against the sample remains constant because it is always touching the surface. So feedback regulation keeps cantilever deflection constant. Voltage required indicates height of the sample. So what is the problem in the contact mode is excessive tracking forces applied by probe to sample. So excessive tracking forces will be applied by probe because it is touch the sample, automatically the force will be applied force will be very high. And there will be one more problem, the cantilever may get damaged. The tip of the cantilever may get damaged. So in contact mode there is two types of measurement. One is constant force. So we can keep the force constant and the feedback system moves tip in Z direction to keep the force constant, and we can fix the height of the cantilever constant. No feedback system is needed, usually used for real-time images, higher scan speeds possible. So these are different methods of measuring the sample surface through the AFM in contact mode. So here the another one type of AFM operation, non-contact mode. Here the cantilever tip will not be touched the sample surface. So in that case the tip will not be damaged anymore. But if we have any water droplets or liquid drops over the on the sample surface, so this will give the unwanted three-dimensional image, or this will not obtain a real topographical or three-dimensional image of the sample. This will also carry the image of the droplet also. So this is a drawback of non-contact mode. But here either neither sample surface or nor tip will be damaged. So van der Waals force will be very low, approximately 10 to the power minus 12 Newton. Fluid layer thicker than the range of van der Waals force gradient. So in this case, fluid layer will be thicker than the range of the van der Waals force gradient. So that's why it also carry the image of the liquid droplets. So in non-contact mode, there will be measurement of attractive forces because both tip and sample surface will be separated. So automatically there will be attractive force between tip and sample. Tip doesn't touch the sample, yes. Van der Waals forces of between tip and sample detected. So what are the problems? We cannot use the samples with liquids because it will it also carry the image of the liquid droplets. So non-contact mode is used to analyze semiconductors. It doesn't degrade or interfere with the sample, better for soft samples. So it will not interact with the sample surface. So this will be beneficial for both cantilever tip and the sample. So that's why this method is much suitable for analyzing soft samples. So this is the third one, intermittent contact or using oscillating cantilever. Cantilever will be oscillating over the surface. So this oscillation is high, free amplitude. The amplitude of the oscillation is very high. So tapping mode. So one time it will touch the sample surface during the scan, and other time it will not touch anymore. Then it will touch. So this will, that movement or the oscillation will be there. So sometimes it may have the higher amplitude or reduced amplitude depending on the sample. So very short tip and sample contact. At any it will not touch the sample surface always. So there will be a very short contact between tip and the sample. no lateral force, fluid layer is less detrimental, less damaged. The fluid layer will not make any disturbance during this analysis, because the tapping mode is the cantilever touches the sample surface through the fluid layer. Even though the fluid layer is present, this will show the original surface of the sample in the image. So that this is a diagram for tapping mode, a intermittent contact. So there will be a much deflection in the laser beam cantilever tip. This deflection will be piezoelectric scanner will monitor, and it will convert into force, and that force will be converted into electrical signals. So this oscillating amplitude may differ. There will be a large deflection or shorter deflection depending on the requirements. So tapping mode AFM. In tapping mode, AFM tip vertically oscillates between contact sample surface and lifting off at a frequency of 50,000 to 5 lakh cycles per second. Oscillation amplitude reduced as probe contact surface due to loss of energy. This oscillation amplitude may reduce because while touching the sample surface, the cantilever tip may lose the energy. So over the time, the oscillation amplitude may get reduced. So what are the advantages? This overcomes the problems associated with the friction, adhesion, electrostatic forces, more effective for larger scan sizes. So this is almost the advantages over contact and non-contact mode. Contact mode, either sample surface or cantilever tip may get damaged. In non-contact mode, it will carry unwanted the fluid images also. So these will be overcome by intermittent contact tapping mode. So usually the cantilever tips have the smaller curvature, very sharp tips 10 to 20 nanometer, high aspect ratio. Usually the aspect ratio will be monitored by through length by breadth. So if we have high aspect ratio means sharper tip, robust, resist damage when in contact with the surface. So it should not get damaged when the tip is in contact with the sample surface. So these are the requisites for cantilever tips. And resolution is based on the tip size and shape, small scan size, small scanner displacement. So this will govern the resolution of the images. So operation, there will be a sample holder. Sample material will be fixed to metal disc. Then it is the snapped to position on the top of the scanner assembly by the action of magnet. Then there will be an optical microscope to correct the position of the probe over the sample surface, and there will be a piezoelectric materials to move the probe over the surface, and the probe assembly is lowered to the towards the sample surface using feedback control system. So the parameters like scan area, probe force and scan rate are the input of the system, and the scan is put into motion. Successive line scans or rasters are combined to generate a three-dimensional image of the surface. So there are two generic configurations for scanning. So sample may be fixed stationary or the reverse configuration. The cantilever, the probe may be fixed constantly. So there are two modes of operation. Either we can fix the sample position constant or cantilever position constant. So this is a simple operation. So numerous computer programs are available for image manipulation. In contact mode, imaging a soft deflectable cantilever with a sharp tip is brought close to the surface. The force calculated based on the Hooke's law. That force is monitored through the deflection in the cantilever tip. That will be again converted into images through electrical signals. So you can fix the force constant or height of the cantilever tip constant through the as maintained by the feedback loop. The magnitude of the forces applied to the tip range from in a constant force type. So we can apply the force range from 0.01 to 100 nanometer. So piezoelectric elements are there. They hold and position the sample in all three spatial domains x and y, x, y and z, and participate in the feedback loop process. A three-dimensional rendition of the photography of the surface is achieved by the contact mode of the AM. So every mode is have their own advantages. So contact mode, high resolution image we can obtain damage will be caused to the sample. We can measure the frictional forces also. In non-contact mode, low resolution but no damage to the sample. Tapping mode, better resolution, minimal damage to the sample. So overall we can conclude like this. Contact mode we can get the high resolution, but there will be a possibility to damage the sample or to damage the cantilever. Okay. Non-contact mode, low resolution images but no damage. So better resolution with minimal damage will be obtained in the oscillating cantilever or the tapping mode AFM. So these are some of the AFM images obtained for titanium oxide and zirconium oxide nanoparticles. So with this I wind up this presentation. So we will see another type of scanning probe method in the next lecture. Thank you.